Hi, I'm Srivash, and we are NMIT's first ever space rover team. And we work under the umbrella for the Center for Robotics Research. We are designing and building a rover for the ISRO Let's Build a Rover Space Competition 2024. Our team is a multidisciplinary team of 10 members, and we are divided into 4 subsystems, namely the mechanical subsystem, electronic subsystem, communication subsystem, and the software subsystems.
In the front of a rover, we have a manipulator arm with 6 degrees of freedom. It has grippers on the front which are capable of picking up objects of decent weight and mass. We also have different mounts for our sensors and our electronics which are safeguarded within the aluminum chassis. Our wheels are of 200 plus mm in diameter with crossers capable of digging into sand, rocks and wood. Our rocker and differential bar design is to be allowing all the wheels to maintain contact with the ground. Each wheel has a drive motor and a steering motor capable of turning in all directions 360 degrees so that a rover can traverse in all directions. Our wheels are designed to drain sand, dust and any other particulate matter that gets accumulated within them. This allows for less damages occurring to the system and the motors, and this shell protects the motors from any kind of impact as well. The arm can be fitted with any kind of end effector. Wheels can be swapped out with ease, and it has high serviceability. So this project aims to be able to create a platform which allows for multi-purpose use case scenarios.
The arm is controlled using dynamical motors. We use inverse kinematics using a camera called Pixie camera, which helps us get the coordinates of the package that are needed. Now let's head on to the navigation. For navigation, we use an algorithm called SLAM, which stands for Simultaneous Localization and Mapping. It helps us to know at which position we are at any point of time, and it creates a map around it, getting to know the environment more. For this, we use a LiDAR and a camera. The LiDAR gets the values of everything around it in a 360-degree view to create a map using an algorithm called Hector SLAM, which just uses the LiDAR data. And the camera which we are using is called the Intel Real Sense Depth Camera, which gives us the depth of a frame it's looking at. So we use this camera for navigation and mapping. So after the LiDAR maps the surroundings, we use the camera for getting any dynamic obstacles that are moving around in the area to avoid them. And the rover has two basic navigations, one where it walks straight, and then to turn left and right, it can do a skid steering or a crab walk. Let's talk about obstacle detection and avoidance. The obstacle detection can be separated into two ways. One is the craters, which has a depth, and one is the obstacles which have a height. For detecting obstacles which have a height, we use the LiDAR. The LiDAR detects any object at a greater than 150 mm and it avoids them as it comes into its perimeter. We use the camera to double check it, and once the object is nearer to the rover stops and goes around it. To check the depth that are craters, we use the camera that is mounted at the front, the Intel depth camera. We get two frames from the camera, one is the normal image frame and one is the depth frame. There are 3 points located on the frame which helps us to know whether the image we are looking at has a crater. Since if the image has a crater, the distance will be more. So if it detects a crater, the rover again stops and goes around the crater for avoidance.
communication between our rover and the base station that we are going to communicate the rover with, we'll be using Wi-Fi communication. We'll be setting up a local area network, and we have opted to go for a 2.4 GHz frequency instead of a 5 GHz frequency, which is available in the Jetson Hornet, because it has a wider range of up to 50 meters, and it also we don't require the speed boost from 5 GHz of speed. Our rover has three switches. One is the main switch, which turns off the power for all components and all actuators in the rover. Another one is a switch that is dedicated specially for a single boot computer, just so it doesn't get damaged from any electrical fluctuations. And the third one is our emergency kill switch. We use that emergency kill switch to turn off all the actuators in our rover, and it is a requirement set by ISRO for this project.
The team has performed many tests and analysis on the rover to improve the functionality of the rover. At present, we are working on integrating the control system sensors to perform a more autonomous navigation of the rover. As future prospects, Nmit will look forward to participating in the University Rover Challenge, which is a competition and a platform for international robotics competitions. We are Team Shourya.